Okay, the problem is that I'm going to be typing the most of my... Okay, thank you. So, I'm Alejandro Infante. I come from Chile. Now I'm a master's student at Department of Computer Science of University of Chile. And, well, you have both of my emails, and I will present about Spy. So, Spy dynamic analysis at the reach of everyone. First, I'm going to introduce Spy, that is a framework for building customized profilers. Then I'm going to spend like a minute in Japao, because I don't have that much time. And then I'm going to talk about how Spy works in my thesis, and a little bit of what is my thesis and the research behind it. So now I'm going to show an example of how to use Spy and what is the power of Spy. Yes, please. So, do you see the fonts? Okay, so I'm going to start like generating a new profiler. Just call Spy, generate, and for this example I choose a test coverage application. So, who has used a test coverage here? Almost all of them, all of the people. So, a test coverage basically records which methods has been executed and which methods didn't execute in the run of the test. So it's useful to know if our tests are really testing the whole application. For this, we need to record every method execution in the test. So how a profiler do that? Well, Spy works instrumenting all the methods. So we can execute our code on each method execution. For this, the code for generating a profiler creates 4 classes. The first one represents a profiler, and then we have instances for classes, methods, and packages. So this represents a method. And what a method in a test coverage has to know? Well, it has to record if the method was covered. It's covered. Okay. So once we have this instance variable, we go to create an accessor, and we create the initialize. So by default, is covered is false. So now we have the basic structure. A method now holds the state of if the method was covered or not. And how do we insert the code? Well, basically we have this method before run within that is executed before each method execution. In Spy we support before run within, after run within, would be like a round of aspect theory, and intercept the return value and a lot of more methods. So here, before each method execution, we are just going to say, well, it's covered, is now true. So now we are going to start to try our profiler. How do we do that? Is just call the profiler, my test coverage, and then just profile a block in a class. In this case, we are going to choose RTView and one of the most simple code, RTView new. So this executes instrument RTView, executes the code, and then clean the system. And now we have the profile of that code. So how do we inspect this? Just go to the RTView, going to grow this window, and then with all the methods, we can have the whole list of methods. Then we are going to see open with menu. We didn't open any window, so the value of is covered is false. But if we go to initialize, that is called by default in the new, we're going to see that it is true. So this is now is a functional profiler. It does everything that a profiler needs to do, but still not very useful because the inspector is not comfortable enough for this. So let's try to enhance a little bit the API. So we go to a class. I want to ask a class, hey, which are the methods that were executed? So let's implement covered method. And that's just query for all the methods and select the ones that were covered. So now I can call that method. And I got a list with just 3 methods that were the ones that were executed. It's interesting because we just call new, but we got initialize content, and set canvas. We didn't got new because new is implemented far upper in the class hierarchy. So we are not instrumenting that. So if we try this code with a larger project, for example, my test coverage run test on package matching, and I'm going to choose Trashell because it's the backend of Russell, and then I of course misspell this on packages matching, again misspell, so I'm going to use just the package name. Okay, testing. Of course, this always happens when you want to try to do something alive. Run test on. Yes, so let me look at the API. Here you have the S2 profiler, that's the main class, and you have a lot of things. So here you have for profiling, that receives a block, running the test, and start profiling. So you can actually say tell a profiler, okay, start and just keep profiling until I send stop. So you can actually instrument like Nautilus, start looking for, with the browser, some interesting things that it's really difficult to like reproduce with code, and then say stop and analyze the profile. So I'm going to use running on test, run test for package name, and yeah, the problem was I was using on instead of for. So now I got lots of classes. So it's really difficult to see some useful data just by querying class by class or something like that. So now I'm going to show you a visualization. But to create this visualization, we are going to use Russell in something in a form that is already binded with Spy. Just create this method, visualize on, and you automatically get the view in the inspector. So I'm going to use Mondrian for this. To do this, we create a new Mondrian. We assign the view, and then we start adding nodes. For nodes, we are going to use the classes. So solve all classes. And for each class, we are going to draw the methods as inner boxes. So B nodes, so class, all methods. Then a little bit of layout, grid, and outside also a layout of grid. Then build, and then we have a basic visualization of the state. So, well, that's almost the same. We just have the classes, the methods. But with the shapes, we can put the information, the relevant information. So, for example, for the methods, we can say before defining the nodes. Add a shape, a rectangle, but adding the color borders by default as red. But if the method is covered, then the color border is black. Okay, message sent but not implemented. Oh, color black. I think it's border color. Yes. So now I execute the profiler, and we have now colors or our methods. So we have methods with high coverage, that is this test class, and method with a little bit low coverage, like tier morph. So one interesting thing is that this class has 100% coverage, but it's a test. It's normal that it has 100% coverage. So let's treat test differently. So I'm going to say if the method is a test, then the border color is going to be green. And for the classes, shape rectangle, I'm going to say the same. Okay, thank you. Also, I need to put the E. So, now with this visualization, I actually would like to get the class hierarchy in there. So for that, we just need to add 2 lines. Yeah, 2 lines. Just add edges. Connect from the class. And just modify the layout to use a tree layout. And out of the box, I got the class hierarchy. So now I can see the coverage of the hierarchy. And some of these, for example, this tree hierarchy is not covered at all. So, also something interesting you can see in the first example. So we have 3 methods execution. That means that this method initialize call the other 2 methods. So we need a way to represent that in the visualization. For this, I'm going to show you how to get the local senders. We create an instance variable, and the same as before. We need an accessor, a default value. In this case, as set. And in the before run, we just get the sender. So, I'm going to use a temporary variable. And the sender is just calling spy sender. And we get the spy map. Or no. So we need to take care of that. Because the spy sender just gets an object, a method that is in my domain. So if we just instrument RTView and is called by the inspector, it's not going to recognize the inspector at the proper sender. So it's going to look in the stack for some other method of RTView that is called. So in this case, the sender is not new. We are going to add it to the local senders if it is on the same class. For that, we're going to just go into sender class spy. It's the same as salt class spy. Picture, just add the sender. let's try this code. Well, we don't see any difference. We have to code it. But it's relatively easy. Just here, we add edges to the code. Connect from all local centers to yourself. So now each method is going to have an edge to each of the local centers. So when we reload this, local center, okay. So now we have an edge to each of the centers. Just let me configure the tree layout. And here we go. So one question is, this code is a kind of complicated code that uses set, go to the module, get the center. What code can we put there? Well, actually, almost any code. For example, one thing is I will try to put the code that I'm instrumenting inside the before run because so it can cause an endless recursion. Well, we have put a cheat for that. So I can just create a RTView. Actually, I can inspect it. And then I'm going to try to profile again. And I got the inspection of these three RTViews because we call three methods. And let me get rid of this because if I execute some other test, I'm going to generate a new window for each of the method executions. So I can crash my system because of the number of windows. So let's look at this bigger example. For this, I'm going to go to create the storage and use the start on method. So I'm going to start on classes. No, start packages matching Nautilus. So now Nautilus is instrumented. If I start looking these things, the compiler is storing. How I can know that Nautilus is instrumented? Well, I can go to the Nautilus package, start looking at the Nautilus code, and I see some weird things. This is the method grabber that we installed on that. And when I call stop, okay, I made a mistake because this is not an instance, this is a class. So I'm going to call, I need to retrieve the instance of the all instances. This is my mistake again. So all instances. Yeah, it's this one. It's the big one. So here I can call self stuff. And everything is normal again. So I even lost the reference of the provider. I screwed up something that shouldn't happen in the presentation, but I'm still able to clean the system. So I have to set this allowed. There are a couple of things that you can do, like instrument array. Block closure is also out of my reach, but I can spend a great part of the system with this. In the morning, I got a test coverage of the collection, all the collections of classes without much problems. So I'm going to leave it here. I think for Spy, just saying that I can also instrument slots. It's a variable accessing and writings. Also, for example, all the string creations or points creations, and get some statistics from there. And also, with all the safety that Spy is ensure that it's not recursion, it's recursion safe. Also, if an exception happens in a place that is really dangerous, it's going to catch it and throw it to avoid crashing the system. So now I'm going to continue with my presentation, the PowerPoint. Thank you. show. About is test coverage application. The thing that I want to show you is that we made an integration with Jenkins. So you can actually put Habao in Jenkins and start building, and you get a test coverage report just in Jenkins. So here we have the test coverage of Russell, and we have all the classes with all the methods. Also, it is available with the reports to download Moose image with an open visualization of Habao. And if the internet connection supports me, we have a live version of a Russell visualization in the web with Habao. Just here we see part of the visualization. RT histogram set, and I think the internet doesn't allow me to drag, but you can navigate the visualization through the web from a continuous integration service. So, yeah, I think that's better, because it was just passing slides on time, so that could be bad. So now I'm going to spend the last, I think, 5 minutes in talking about my thesis. So my thesis is shareable objects. Great. So what are shareable objects? It's objects that we don't need. The idea is that our objects, there are a lot of objects that don't need to be created, or that in some moment of the execution are not needed anymore, because there is another object that can fulfill its behavior. So let's look this little example that is in Java. I'm sorry, but this was for an example for my one of my advisors that is not in Smalltalk. So we create an element, and to that element we assign a default color and a point. So when we start creating elements, they look like this. And then this method is called maintain. So we start creating and creating and creating, and they all look the same. So we propose two fixes of this memory bloat problem. So one of them is creating a cache for the colors. We just cache the colors. And the other one is create a cache for the whole element. So the representation, the object representation looks like this. So in the one at the left, we have duplication of elements and points, and we share the color. And in the other one, we share the whole thing. So which one is correct? At the beginning, we would think that the one at the right is correct because it saves more memory. But do we know how these objects behave? For example, let's say that we use this element to represent a button. What happens if we can change the color of that button? Do all the buttons change of color? Does these elements mutate? So, getting to a refactoring or a fix without knowing the invariant of the program is actually not possible. So we start working on this, and we get to the shareability definition. So we say that two objects are shareable if making all the objects pointing to a first object point to a second object, and the program invariant is preserved. Nothing breaks, in short words. So if you see the picture, the object 1 is no longer needed, no one references him, and the garbage collection can collect it. Even more, if we can identify this object 1 to be not needed at the beginning of its existence, we can just avoid its creation. Not lowering the memory use, but also we save a garbage collection time. But really, this definition is not possible to put into a profiler. I can't say a profiler, hey, like check if D is moving all the references to this object, go to the object works. Actually, that would take ages, and probably it would be impossible to predict that kind of behavior. So we get to a new definition that we call equivalence. And this equivalence definition is our best shot to represent this higher definition that is shareability. But this with a concrete formal definition. So, two objects are equivalent if, well, first, these things that we are going to work through. First, if they are the same objects, they are equivalent. No more words. But if they are not the same object, they have to be instances of the same class. They have to have equivalent instance variables. We don't require them to be the same, but at least equivalent. And no identity operation calls to them. So we can't ask the virtual machine, do me the favor of recognizing between them. And also, they have to be immutable. Why this definition of immutability? Like for all instance variables and some game with the time, is because in Smalltalk we can define immutability. And we don't have constructors. We just have like classing methods, factories. So using dynamic analysis to capture this is really difficult. So we need a heuristic to know which objects are immutable and which aren't. In this case, all this definition says, our heuristic is that an object is immutable if the instance variables are changed only once. So it was nil at the beginning. If you change it once, it's okay. One more and more than once, it's broken. This has some advantages. For example, lazy initialization. So you can capture if an object is lazy initialized, don't actually break the immutability. On the other hand, we have some problems because some objects are initialized with some value by default, and changing that value just a line after marks them as mutable. So it's a trade-off of precision that we are doing. For now, this is our most representative definition. What do we want to achieve with this? Well, our impression is that two objects are equivalent if I cannot distinguish between them in the whole execution. So, how I can ensure that they can be distinguished is because they are instances of the same class, they have the same state, the state is preserved, what we call immutability, and also I don't cheat as in the virtual machine. That is the idea behind this formal definition. Now I don't have time, well, I haven't planned to have time to review this definition to cycles because it would be too much for this presentation. But it's kind of the same idea, just working without it's not a completely recursive definition. Has the proper breaks to get rid of that, but still identify possible equivalent cycles. Well, this is planned to be my thesis work. I should be finishing probably May, June of next year. I hope so. I'm running some experiments, so if you have a parallel program and you have a nice benchmark and you want this tool to be executed on your program, please let me know. I'm looking for data. That's pretty important for our research, and I think it's a really nice tool. I have found some interesting things in parallel that I will be sharing with all of you when I have concrete results and verified results. Thank you. Okay, at this moment, the tool just identify objects that are equivalent. It actually creates the whole object graph and marks the object. Okay, these objects can be shared between them. Also, we are getting the context of creation of the object. So maybe there is a cache that can be put in the object creation. Our idea is to also find new strategies of how reduce memory consumption based on the object graph. So we are going to try to identify patterns in how our profile looks like and just work this before the user has to even open the report. The report is going to be, we have found objects belonging to this pattern, and this pattern can be solved using this strategy. Sometimes it's going to say, you can insert a cache in this method, in this line, and everything is going to work. And in other cases, it's going to say, well, it's instances of this class is created in these places, but the fix is not that straightforward. But yes, we are going to do looking for patterns of how can we solve this, and run them between how easy is to solve it, how hard is to solve it, and try to help as much as possible to the user, because it's not immediate, all the solutions.
So yeah, it's like the idea is to implement this complement for your development, or to do an improvement of the virtual machine and the compiler.
No, this is a tool that anyone can run on a perfect image. My thesis is about how to take big software, it's really complex software. It's not really possible to code review everything to look for unnecessary use of memory. So this tool is supposed to guide you through reducing the flow of memory, because these are not memory leaks, so it's not easy to identify that there is bloat. Usually with memory leaks, you let the application running, and it's run out of memory. But here, you could think that everything is okay. Oh, it's just running, it's just using a lot of memory. But I'm not sure that that's bad. I'm doing expensive stuff. And with the Russell, it happened that way. We had some objects that were allocating too much space that could be reused, but we thought at the beginning that it was okay to have that amount of instances. And then we found, okay, they are not needed. Yes, we are going to work with cache, flyweights, and one thing that we are going to, it's really early, it's about partial shareability. So part of the state can be shared, part of the state cannot be shared. It's kind of flyweight, but instead of this object being part of flyweight, maybe split this object using a flyweight.
How about this open source? It's like free?
Yeah, it's MIT. If you download the Spy, you can go to object profile page or the smalltalk hub. We have several configurations of like Spy2 load, and there is several groups. Like you can load just Spy, the core of Spy, the core of Spy plus the test, the Spy plus the test plus the Russell, or for example, just the core of Spy and Habao for running in a minimum image. So then you can fill out the results or the ECL XML representation for Jenkins, or also Habao with visualization that can also be really useful when you are developing in that image. So you have several options, and they are just published in smalltalk. You can use it, you can modify it,
you can do whatever you want, and we are open to all suggestions. So if you are going to modify it, maybe you should talk with us because we know a little bit more. You're going to lose less time trying to do that modification, and we can get a better tool.